Okay. Section 7.4 is about titrations, and titrations are a way of typically determining the concentration of an unknown solution. So they call these quantitative analysis methods. We're going to be using numbers to determine the concentration of an unknown by reacting it with a solution whose concentration we do know. There are a couple of different general types of titrations. The first one is called an acid-base titration or an acid-base neutralization reaction. This is what you guys are going to be doing. And then the other one is called an oxidation reduction reaction, which is something that they tend to do more in an AP chemistry class, okay? So just to sort of like review what neutralization reactions are, you're going to have an acid reacting with a base to produce a salt and water. Acids typically have a hydrogen ion in them. Bases contain a hydroxide ion. Salts are going to be ionic compounds. And then you know what water is. You should feel a little bit of heat coming off of a neutralization reaction. You might notice that the container that the reaction takes place in may fog up just slightly. Okay, let's turn to the next page. There are a bunch of different types of problems associated with titrations, but mainly you need to have a balanced chemical equation in order to perform any of the problems. There is a little bit of a shortcut, but I just don't like teaching the shortcut because it doesn't work in every scenario. So let's take a look at number one. Here we've got a titration with 25 mils of hydrochloric acid, 15 mils of 0.3 molar sodium hydroxide. They want to know what the hydrochloric acid concentration is. So we start by writing the balanced equation. So it's HCl plus NaOH. We're going to produce NaCl and HOH, and this is already balanced. I would suggest writing the numbers underneath the substances. So you've got 25 mils of HCl. We've got 15.62 mils of NaOH. Its concentration is 0.3 molar. And then we're looking to calculate the concentration of HCl. You start where you have a volume and a molarity of one substance, because we learned in a previous section that if you're looking at the molarity triangle, you can solve for moles by multiplying molarity times liters. So you always want to ask yourself, how can I get moles? And step number one here will be to take our molarity times liters to give us moles of NaOH. So 0.3 times 0.01562 liters, because I moved the decimal 3 places to the left, is going to give me my moles of NaOH. I don't have a calculator on me, so I'm not going to write a number down. Then I need to do a mole ratio from NaOH to HCl. So step number 2 is going to be using the coefficients. So you've got a 1 in front of NaOH and a 1 in front of HCl. And then step 3 will be to take your moles and divide it by liters to give you molarity of HCl. So this is going to be 1 over 0.025 liters of HCl. I got 0.19 molarity. And I rounded it to 2 sig figs because 2 sig figs was the fewest that I had and the numbers that they gave me. Okay, so this is one scenario. Another scenario might be you're solving for liters, you're solving for grams of something. It just kind of depends on the problem. But generally, you're always going to, at some point, calculate molarity of an unknown solution. Okay? Okay. Is that enough for you? Okay. Let's turn the page then. On the next page, they go over the typical glassware that you use in a titration. And we probably will have time to do this today if you want to do this. So typically what you're going to do is, everybody have this down. You're going to have a burette. The burette will be attached to a ring stand using a burette clamp. And I'm going to make some notes on what is in the different pieces of glassware. So here it says that the solution whose concentration is known. This is called the standardized solution. That means the other one is the unknown, okay? And anytime you guys are using a burette, it typically contains the standardized solution. So typically we know the concentration of the solution in the burette. When you record volumes using the burette, make sure you record to the hundredths place. Okay, let's come down here. So what's going to happen is you typically use a pipette to measure out a certain volume of the unknown, okay? I've got a digital pipettement over here, and you put it on the top and you literally press a button and it sucks it up for you, and you press another button and it spits it right out, okay? So the pipette, which these two are examples of pipettes, they usually come in different volumes, like a mil, 5 mils, 10 mils, it just depends. And these are also very precise, and they deliver the unknown into your Erlenmeyer flask, okay? So in your Erlenmeyer flask, what you will have is the solution of unknown concentration, and you have to add something called an indicator. If you forget to add the indicator, you will never know when you're done with the lab, okay? So this right here is extremely important. The indicator that we pick is based upon when we expect the moles of acid to equal the moles of base inside of that flask. And some of the indicators, they don't change color at exactly the same place, but it's around the same place, so that's why we use it. Okay, so here it says that the indicator changes color when the reaction between the moles of acid and the moles of base is complete. So the color that we're going to change to is going to be a faint pink, like baby pink as you could possibly get. If you put a piece of white paper underneath the flask, it's easier for you to see when that solution turns pink and stays pink. Because you have to swirl the flask while you're doing it. It'll start to turn pink, and you'll think that you're done, but then the pink color goes away. So once you start getting close, that's what happens. And you get to a point where if you let a drop hang from the burette and you don't let it fall, but you get that drop with the side of the flask, that's actually considered a half drop. You could actually change the color of this solution to pink by just letting a half drop fall in, okay? If you go to hot pink, that means you went a little too far. Your solution's a little too basic. The indicator that we're going to be using is called phenolphthalein. I think this is how you spell it. It's kind of complicated thing to spell. You will often see phenolphthalein abbreviated as PPT. Okay. It's colorless. when it has a pH less than about 8. And then it turns pink around 8.1 or so. And that signals the end of your titration. Okay, if it goes to a hot pink, you're probably at a pH of like 9, maybe 10, depending. Okay. All right, now let's take a look at the next page, the last page. So your setup for the titration will look just like this with your ring stand, with your burette clamp. Your burette is in there. And then you're going to be dropping solution of a known concentration into the solution of unknown concentration. And then when it turns, and then swirl it as you're doing it. And then when it turns faint pink, you are done. Okay, be really careful on your definitions of equivalence point and end point. People often mess these up. The equivalence point happens when the moles of hydrogen ions equals the moles of hydroxide ions. Your indicator that you use, depending upon the kind of titration that you're doing, may or may not turn color exactly at that point. It may turn color just slightly after, like ours does with phenolphthalein. When the indicator changes color, that's when you're allowed to call it the end point. Okay? And that's when you stop. Okay, any questions for me on this?